Okay, so where were we? We're naming the number here using words. And so recall we have the ones place, the ones periods, the hundreds periods, the thousands, the millions and billions, and then trillions. Okay, so we're going to go through each one. So, okay, so this one would be 8 billion. So 8 trillion, I'm sorry, trillion. So that's this here. 165. 5 billion, right? That's this guy. And then 432 2 million. Okay. And then 98,000. And then 710. Sorry, that's supposed to be 10. 10. Okay, yes. Okay, so that's our super fun example. Oh, and that's, again, super fun solution. All right, so remember to go, so going in the other way, if we were given the number as a word, we need to identify the words that indicates periods. We draw 3 blanks to indicate the number of places needed in each period. We separate the periods by comma, and then we name the number and place the digits in the correct value position. Okay, so super fun example, write 9,246,073,189 as a whole number using digits. So let's go ahead and look at that. So this would be in the billions, you have 9, so that's that's 9 billion. In the millions, there's 246 million, so that goes there. The thousands, there's 73,000, so that's 73. There's a 0 in the hundreds place of the thousands. And then 189, so the number would be 9,246,073,189. Okay, so how about rounding? So let's talk a little bit about rounding. So, when you want to round a whole number, you locate that given place value, mark it with an arrow, and all the digits to the left do not change, and we underline the digit to the right. And then we ask ourselves, is this digit greater than or equal to 5? And if it is, you round up, you add 1. There should be a 1, not an 11. I don't know why that says that. And if not, we do not change. We stay the same, okay? And then everything to the right of that given place value that you're rounding to becomes zeros. Okay, so let's do a super fun example. We have 23,658. Let's round to the nearest 100. Okay, so we're rounding to the nearest 100. So this is our point of interest here, the 6. So we look next to it. We underline that. So immediately to the right of the hundreds place is a 5. And since it's greater, we round up. In other words, this 6 becomes a 7, and then everything else becomes zeros. Okay, so let's go ahead and round the following. Oh, this is a typo here. Sorry about that. So round 103,978 to the nearest 100,000, 10,000. So for part A, the hundreds right here. Okay, so we're going to round this number, but we're looking at this one, right? So then for that, since it's higher than 5, this is going to go up. But because this is a 9, it goes up to 10, and that changes this one to a 4. So actually the nearest 100 would be 104,000. Okay, and then the nearest 1,000, okay, so looking at the number again. So if we're running to the nearest 1,000, this is the number that we're going to either keep the same or change. So then we look at the one next to it. The one next to it is greater than 5, so we round up. It's actually the same thing. Okay, and then here, the nearest 10,000. So let me just write the number again. Okay, this is the 10,000s place. I look at this one, so I'm rounding this, and I'm looking at this to see if I go up or down. It's 3, which is below 5, so I stay the same. So then everything becomes, this is a 3. This stays the same, so this 0 stays the same, and then everything else becomes zeros. Okay, so that would be 100,000. Okay. Oh, and I'm pretty sure, yep, I did that again. So this is the nearest 100 is 104,000. We just said that. Oh, let's see here. This is 104,000 again. And then 100,000 is to the nearest 10,000. Okay. So next thing is to identify multiples and apply divisibility tests. So first of all, what are multiples? So let's say you have the number 2. What's a multiple of 2? If we were to count by 2s, those are the multiples of 2. So like 2, 4, 6, 8, right? Those are multiples of 2 because you can be rewritten as the product of a number and 2. And similarly, multiples of 3 can be rewritten as a product of a number and 3. Another way to think of it is just counting by 3s. Then you're also saying, okay, 3 the first time, then the next one would be 6. I said it twice, add one more, add one more 3, which is 3 times 3, that's 9, and so on, okay? So here's some common multiples, okay? We have, 2, 4, 6, 8, all the way to 24, 3, 6, 9, 12, right? And then here the 10s, 10, 20, 30, 40, 50, 60, 70. So it's helpful to be, aware of these and to be, just to have these in mind because we're going to be using them later. Okay, so let's see here. Another way to say that another number, let's talk about divisibility. If you want to say 15 is a multiple of 3, you can also say that 15 is divisible by 3. Okay, so that means that 3 divides into 15, or 15 can be divided by 3 evenly, okay? So one thing is, if you have a number that is a multiple of a different number, then that first number is divisible by it. So let's say if 24 is a multiple of 3, then that means that 24 can be divided by 3, okay? And then you might be thinking like, who cares? But let me just tell you, we are going to use this. So it is really to your benefit that you become like super comfortable with this concept, okay? Okay, so there are some common divisibility tests. So we have here, if you notice the multiples of 5, they all end in 0 or 5. So there's some rules, okay, with some common numbers. We can say the number is divisible by 2 if it's even, or if the last digit is 0, 2, 4, 6, or 8. Number is divisible by 3 if the sum of the digits is divisible by 3. So what does that mean? So let's say 12, okay? Is 12 divisible by 3? Well, 12, let's take the digits 1 and 2. So 1 plus 2 is equal to 3. Yes, that's divisible by 3, and 12 is also. Okay, let's see what else. If the last digit is 5 or 0, it's divisible by 5. 5 goes into it. If it's divisible by both 2 and 3, it will also be divisible by 6. And then, of course, if it ends with 0, it's divisible by 10. So, question for you is 5,625 divisible by 2? No, because it does not end with a 0. How about 3? So not 2. 3, let's see, add it. So if we add 5 plus 6 plus 2 plus 5, that would be 11 plus 2, 13 plus 5 is 18, which is divisible by 3. So yes. A 5, it ends with 5. So yes. By 6, no, because it's not divisible by 2. How about by 10? No, because it does not end in a 0. Okay, so this is divisible by 5 and 3. And it's really helpful because this leads us into factoring. So prime factorization, let's say here, we're going to talk about that and least common multiples. So when you say when you say 72 divisible by 9, for example, you can also say that 9 is a factor of 72. In other words, what are factors? Is here 8 and 9, 8 times 9 is 72. So these numbers that I multiply together to become the product, which is 72, they are known as factors, okay? So it's really to your benefit to be super comfortable with the word factor because we're going to be factoring a lot, okay? We're going to be taking numbers and breaking them apart and studying them and then putting back together again sometimes. Okay, so let's say, for example, what are other ways to factor 72? You have 1 times 72, 2 times 36, 3 times 24, 4 times 18, and 6 times 12. Okay, so 72 has all these factors, okay? Not all at once, right? They're paired differently, but these are all numbers that divide 72, okay? All right, so let's see here. We have an expression A times B. A and B are called factors. If A times B is equal to a different number, M, and both A and B are integers, then we say that A and B are factors. Okay, so factors are integers. Let's see, what else can we talk about? Prime numbers. This kind of begs the question, like leads us to prime. Okay, it's a counting number that's greater than 1 where the only factors are itself and 1. Okay, so let's think of some examples of primes. Okay, so 2, right? The only factors of 2 are 2 and 1. 3, common prime, right? 5, what else? 7. Is 9 a prime? No, okay? Because what? Because you can't, 9 is divisible by 3, so that's not prime. Okay, and so on. And then composite is basically anything that's not prime. So your numbers, your counting numbers consist of primes and composites. Okay, so here are some common numbers. Look at the numbers 2 through 19. And there are the list of possible factors, right? Possible divisors. And since, look at the ones that only have 1 and itself, those are prime. Everything else is composite. Okay. All right. The only even prime number is 2. That is correct, right? Why is that? Because after 2, any even number can be divisible by 2. Remember, the even numbers end with 0, 2, 4, 6, and 8. So that can all be split in half, hence not prime. Okay. Okay, so any composite number can be written as a unique, meaning that there is only one way, product of primes, okay? So since this is unique, this has a special name. This is called a prime factorization of that number, okay? So we really need to be super familiar with this, also be very comfortable with it, get used to the terminology, like settle in, okay? When I'm doing prime factorization, I'm taking a number and I'm breaking it apart into all the possible primes, and the product of these primes give me the number back. Okay, so let's go ahead and do some. So let's see here. To find the prime factorization of a composite number, we find 2 factors of number and use them to create 2 branches. If a factor is prime, the branch is complete. And if it's not prime, you keep going. So let's go ahead and do that. So 48. Let's do the prime factorization. So 48 is 4 times 12, yeah? Well, that 4 can be broken down into 2 times 2, and that is prime, so I circle that. 12 can be broken down into 2 times 6. 6 is not prime because you can write that as 2 times 3. And now you have a product of prime. So 48 is equivalent to 2 times 2 times 2 times 2 times 3, okay? So let's go ahead and do the prime factorization of 80. Okay, so 8 times 10, that's one set of factors. Now note, you can go, you can start anywhere with any 2 factors and you'll get the same prime factorization in the end, okay? So for 80, my prime factorization is 2 to the power 4, or in other words, 4 times 5. Okay, so that's it. Let's see. Let's do 252. Okay, what's the prime factorization of 252? So 252 divided by 2 is 126. Divide that by 2, 63. 63 divided by 3 is 21. And then 21 is just 3 times 7. Oopsies. I'm just over here. 3 and then 7, because I don't know, for some reason it doesn't let me draw. Okay, so the prime factorization of 252 is 2 times 2 times 3 times 3 times 7. Notice that I go from least to greatest, okay, counting repetitions. Okay, so why do we care about primes and multiples? Okay, we use this to find what's called the least common multiple of 2 numbers. This is when we add or subtract fractions, so it's very good to be comfortable with this method, okay? So let's suppose we want to find the least common multiple of 12 and 8. So 12, if I count the multiples, it's 12, 24, 36, 48, 60, 72, and so on. 18 would be 18, 36, 54, 72, 98, and 108. What multiple do they have in common that's the least? Well, that's 36. That's the least one. So that's why we call that the least common multiple, okay? LCM. LCM. Okay, so the LCM is the smallest number that is a multiple of both numbers. Okay, so, you know, listing multiples is usually the easiest way to do this. Okay, so let's go ahead and do the common multiple of 15 and 20. Okay, so 15, it would be 15. Let's list the multiples: 30, 45, 60, 75, 90, dot, dot, dot. Okay, 20, 40, 60, 80, and then hold the phone. See here, I already see one in common. So the LCM is going to be 60. Okay, let's go ahead and do the least common multiple of 9 and 12. So 9, 18, 27, 36, 45, dot, 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 12, 12, 24, 36, 48. Hold the phone. These are common. So my LCM for 9 and 12 is 36. I mean, the section 1 through 69 odd. So we know what the odd numbers are, right? 1, 3, 5, 7, 9, dot, 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 dot. Okay? All right, good luck, and I will see you on the next video.